Okay, I think we're going to get ready to roll. We've got to 7 minutes past. So a very warm welcome, and here we go. I'm Simon Leeks, the publishing manager for Ruskin Mill Trust and a researcher for the Field Centre. And this month we are delighted to welcome Troy Vine, who will be presenting on Goethe's Polemics against Nature, a morphological approach to history of science. Troy received his doctorate from University College near Chicago. He intensively studied Goethean science in America, then moved to Berlin to undertake a second doctorate, this time in philosophy at Humboldt University. He has published on Newton, Goethe, Wittgenstein, Barfield, and Bortoft. Troy is the program lead for the Holistic Science MSc at Schumacher College. He is co-editor of the Holistic Science Journal and an associate researcher for the Field Centre. After Troy's presentation, we'll have a discussion. If you'd like to ask something or have a comment, then please put it in the Q&A box. The Q&A box should be on the right-hand side. Try not to pop it in the chat instead. And then we'll bring all of those together and put them to Troy at the end. So Troy, without further ado, we're delighted to have you with us, and it's over to you.
Lovely, thanks, Simon. It's just got very dark here and started to pour the rain, so I hope that doesn't bode too ominously for the talk. So the talk that I'm going to be giving today, it has a title, Goethe's Polemics against Nature, Newton. But it's actually the subtitle that is in some ways more interesting for this particular talk, a morphological approach to the history and philosophy of science. So what does that mean, a morphological approach to the history and philosophy of science? So what I have in mind is what happens if we apply Goethe's method to Goethe himself. So Goethe developed a method, the morphological method, for understanding nature, for understanding plants, colors, humans, animals. And so the question that I want to pose is, well, can we apply it to other things too? In particular, can we apply it to the history of science? And if we do apply it to the history of science, what insight does that give us? What does it help us maybe understand that we didn't understand so well before? And my claim in the talk is that it helps us understand Goethe's polemics against Newton. So I'll talk about Goethe's polemics against Newton at the end, but in some ways, what's just as interesting is how do we get there? So if we want to critique somebody, or if we want to understand someone's, polemics or argumentation, if we want to understand what one philosopher is saying about another philosopher, or one scientist is saying about another scientist, how do we even approach the question of assessing what they're saying? And this is obviously an important question for the history of science and the history of philosophy. And so in some ways, my claim is quite controversial. So I'm going to claim, another title for the talk could have been, is Goethe a Newtonian? And I want to suggest that the answer is yes. But I also want to suggest that the caveat is that we have to understand Newton very different, or we have to, in a way, reconceive Newton just as we would need to reconceive Goethe to understand why the answer might be yes. So the reason I think that's a controversial claim is because Goethe is often portrayed as somehow outside of the mathematical tradition, that he's sometimes outside of the experimental tradition even, that somehow Goethe is offering an alternative to Western culture or Western kind of science or something like that, or science as has been practiced in the West for the last 200 years. And I want to suggest that this picture is, while seductive, is very misleading. Okay, so my talk is structured in 3 parts. I'm going to begin by just asking the question, okay, what is Goethe's method? What is the morphological method? If we want to apply a method to the history of science, the first question we have to ask is, what is it? So I'm just going to talk about that in the first part of my talk. You know, just so I'm just going to give an overview of Goethe's method in general, focusing on one particular essay, The Experiment as Mediator Between Object and Subject. And then I'm going to pick out kind of 3 people from the history of science, a mathematician, Newton and Goethe, and I'm going to compare what those 3 people said about method and use that as an example of how to apply Goethe's method for observing plants or colors to the history of science. And then in the third part of my talk, I'm then going to look at what does this tell us, or how can this Goethean approach to understanding Goethe, how can that help us understand Goethe's polemics against Newton? Okay, so I've prepared a little slide. Let me just share that with you. Sorry, bear with me, it should be here somewhere. Sorry about this. Seems to have, there we go. Too many windows open. All right. Can you see that? Is that visible? Thumbs up? Thumbs up is good. So, yeah, Goethe's polemics against Newton. So the first part of my talk is going to be Goethe's morphology. What is Goethe's morphology? So I'm just going to summarize 3 key ideas from his essay, The Experiment as Mediator Between Object and Subject. Goethe wrote, this was an essay Goethe wrote for himself in 1792, and he wrote it in response to a very negative review that he had from a physicist about his newly published work on color, his contributions to optics. So in his contributions to optics, which he published after studying color for about 1.5 years, in his contributions, he made a couple of claims against Newton, and a physicist rightly pointed out that these were not tenable claims. And so in response to this review, he, in a way, for the first time, really kind of considered critically his method. So he wanted to understand what his method was, what it can do, what it can't do. And so this is, in a way, the first real statement we have of Goethe's method, which he then published in about 30 years later. Interestingly enough, in 1795, Schiller asked him about his scientific method, and Goethe sent Schiller this short essay. And Schiller's reply was, Goethe said, well, it's a bit old and my thought has moved on a bit. And Schiller said, well, look, why don't you write a newer version? And Goethe said, you know what, I'd rather than write a new version of my method, I'd rather show it in practice. And the result of that was actually his theory of color, his big Farbenlehre, published in 1810. So just from a kind of biographical point of view, this essay played quite an important role. Okay, so the 3 main ideas for Goethe's method, or the 3 main stages, you could say, or the 3 main activities, is the first thing you do as a scientist is manifolding. The second thing you do is seeing connections. And then the third thing you do is come to basic principles. or a basic principle. So I'm just going to go through some quotes about what Goethe says about that. So regarding manifolding, and this is a really important kind of central idea to everything Goethe did in a way, was the statement that I would venture to say that we cannot prove anything by one experiment. So the basic idea is with one observation, with one case, with one experiment, that isn't going to tell you anything, yet alone prove anything. And then Goethe says, as worthwhile as each individual experiment may be, it receives its real value only when united or combined with other experiments. The manifolding of each single experiment is a real task of the scientific researcher. So as a scientist, I would also say as an historian, the first thing we need to do is, when confronted with a particular case or a particular experiment, is we need to look at, okay, what are the other ones? You know, what other cases, experiments are there? And this idea is also reflected in Goethe's work on plants. So if you're presented with, let's say, a plant at a particular stage, the first thing you want to do is to say, okay, how was the plant yesterday? How will a plant be tomorrow? And then to start building some kind of sequence. And with a plant, nature's very nice, living nature is very nice because it offers us kind of sequences in the life cycle of a plant or the growing stages of an animal. You know, we're presented with these sequences because the organism presents itself in time. Color's not so straightforward. So just a word about manifolding. It's a strange term. I've chosen that as a translation for Goethe's term, which is Vermannigfaltigung. In German, that's also a strange term. So, yeah. It's not clear whether Goethe coined that term. There's one instance of it being used, I think, in Jakob Böhmer. So maybe Goethe had come across that term. Maybe he had coined it for his work. One thing he did coin is the term morphology. Morphology comes from the Greek morphe, which means form. So morphology is something like the science of form or the study of form. So form is a kind of central concept in Goethe's work. And also how form changes, how one instant changes into the next instance. Okay, manifolding. The next one is seeing connections, the next stage. Let me just get my notes. So Goethe says, in the first two parts of my contributions to optics, I sought to set up a series of contiguous experiments derived from one another in this way. Studied thoroughly and understood as a whole, these experiments could even be thought of as representing a single experiment, a single piece of empirical evidence explored in its most manifold variations. So this stage is really important. So the first stage is we start off with one experiment, one instance of something, and then we look for kind of related instances, related experiments. And then we need to look at, do we see a connection between them? Can we put them in a sequence so that we can see a connection? And if we manage that, if we manage to see connections, then we can build a sequence based on that experience. And the experience is, in a way, the basis of that ordering. So there's a kind of human aspect to our science. It's based on our capacity to see connections. If we can't see a connection, then that's the end of the story. You know, science stops there for you as a particular person or for the study as a whole. So seeing connections is a really important stage. And also it's not given that one will see connections. And as I'll point out in the next section, you know, in the history of science, there are connections that we just haven't seen. And so, yeah, so seeing connections is so the science isn't the method of science isn't some kind of automatic process where you kind of you have a method and you turn a handle and the result comes at the end, but rather, there's an engagement of the human being and the faculties of the human being. So an interesting question, and this will take us into the next section, is, what does Goethe see his morphological method as being most closely related to? What other discipline does Goethe think have a similar method to the method of seeing connections? And interesting enough, Goethe thinks it's mathematics. So Goethe then says, such a piece of empirical evidence, composed of many others, is clearly of a higher sort. It shows the general formula, so to speak, that overarches an array of individual arithmetic sums. So Goethe is using this analogy from mathematics. We know from school, if you have a formula like y equals x squared, we plug in values of x and then we can calculate values of y. So for each value of x we plug in, there's a related value of y. And so one formula, y equals x squared, can give us a whole series of related numbers. So this is the kind of, so even though all of the different numbers that come out, I mean, there's an infinite number of numbers that you can generate with the formula y equals x squared, but all of those numbers, that one formula relates all of those numbers. So in a way, each number expresses the general formula, and the general formula is also expressed in each number. Goethe carries on by saying, in my view, it is the task of the scientific researcher to work toward empirical evidence of this higher sort. An example of the best men in the field support this view. From the mathematician, we must learn the meticulous care required to connect things in unbroken succession, or rather to derive things step by step. Even where we do not venture to apply mathematics, we must always work as though we had to satisfy the strictest of geometricians. So what Goethe is thinking of here, if we think again back to school, something like Pythagoras' theorem, we take a triangle and we draw some squares on the triangle and we divide them up. We can then have like a series of steps that show how, so we have a series of steps that then prove Pythagoras' theorem, and each step we can see how each step relates to the previous step. Nothing is added, nothing is taken away. There's no leap, there's no unbroken stage in a mathematical proof. So again, this is the picture Goethe has of his scientific method. This idea of each step being, you can see the relation to the step before. So actually, I mean, Goethe also has quite a modern understanding of mathematics as well. Like, he doesn't conceive of it as some kind of disembodied abstract practice, but rather an embodied practice that's bound up with the idea of proofs and that kind of thing. Okay, and then Goethe warns against the dangers of not doing science his way. He has Newton in mind when he says, it is easy to see the risk we run when we try to connect a single bit of evidence with an idea already formed, or use individual experiments to prove some relationship not fully perceptible to the senses, but expressed through the creative power of the mind. So Goethe here is really stressing that the relationship that you see between each part is fully perceptible. Sorry. So this is why I called step 2 seeing connections, because for Goethe it is something that you see. It's not like an imagined connection or something like that. It's something that we see. And then seeing connections is a term from Wittgenstein, based on the same. So in a way, I mean, Wittgenstein once said, I'm applying the morphological method to language. So Wittgenstein is somebody else that takes this idea from Goethe very seriously. The last stage, basic principle. So Goethe says very little about this in the essay. Sorry about that. in the essay, The Experiment as Mediator Between Object and Subject. But right at the end, easy to miss, he just kind of tucks it in when he says, my intention is to collect all the empirical evidence in this area, do every experiment myself, and develop the experiments in their most manifold variations so that they become easy to reproduce and more accessible. So this is stage one. This is the manifolding. Collect all of the evidence, do all of the experiments. Then he says, I'll then attempt to establish the axioms in which the empirical evidence of a higher nature can be expressed. So the evidence of a higher nature is the seeing of connections. And then he says to see if they can be subsumed under a higher principle. So this is in a way the third stage, or the final part of Goethe's method, is once you start seeing connections, to see if there's a single principle that in some ways expresses all of these different experiments and connections that you are seeing. So the general idea is to start off with as many different instances as possible, order them in a certain way, and then come to see them as all of the expression of some single principle. Okay. So that's just a little overview of Goethe's method. So how do we apply this to the history and philosophy of science? So in some ways I've chosen three people to not kind of overdo it with a whole series of scientists. I've chosen three scientists. So I've chosen Pappus, who was a 3rd or 4th century mathematician. I've chosen Newton, and I've chosen Goethe. And I'm going to, in a way, compare their three statements about their method. And then, and then in that comparison, we can then see, firstly, can we see a connection? If we compare their methods in that way, can we see a connection? Can we get to stage 2? And lastly, I mean, 3 is, in a way, not really enough for any definitive answer, but can we start to see a general principle? Can we see some kind of basic principle that is reflected in their different approaches to science or mathematics? So I'm going to take as a foil Henry Bortoft and a chapter from his last book, Taking Appearance Seriously. So in that book, he had a chapter called Goethe and Modern Science. So the question of the book was, or the chapter is how to place Goethe within the scientific tradition. Where does Goethe fit in that? And Bortoft said the following: in the 13th century, Roger Bacon said in his Opus Maius that mathematics was the door and key of the sciences and things of this world, and concluded, wherefore it is evident that if in the other sciences we want to come to certitude without doubt and to truth without error, we must place the foundations of knowledge in mathematics. So this is Roger Bacon. Bortoft continues, it is astonishing how this remark made over 800 years ago encapsulates the one-sided mathematical approach that Western science has worked with ever since. So Bortoft is then kind of characterizing the experimental tradition or the scientific tradition as having this kind of one-sided mathematical approach. He then says of Goethe that this is what Goethe reversed when he returned to the senses and put sensory experience first instead of the mathematical. So here we have a contrast between, in a way, mathematical science on one side and Goethe on the other side. So even though Bortoft, he lists a whole bunch of figures, Plato, Aristotle, Descartes, and Goethe, and he lists a whole bunch of figures, Plato, Aristotle, Descartes, and Goethe, and he lists a whole bunch of figures, Plato, Aristotle, Descartes, and Goethe, and he lists a whole bunch of figures, Plato, Aristotle, Roger Bacon, Albertus Magnus, Robert Grosseteste, Newton, Descartes, the whole list of these kind of famous scientists who worked predominantly on color over the last two centuries. So he has these series, he's put these series in place, and he has a very nice series of the development of the mathematical method up until Goethe, and then you have this break, and then Goethe then is doing something entirely different. So we could say, that for Bortoft, he wasn't able to see a connection between Newton and Goethe. He wasn't able to see a connection between the mathematical method and Goethe's method. So one thing that's important to note in the context of Bortoft is that in some ways, I'm not singling out Bortoft because he's a bad philosopher or a bad historian, but on the contrary, I'm singling him out because he's a particularly good historian, a particularly good philosopher. And the fact that somebody's sympathetic to Goethe and somebody that's done so much to make Goethe's work understood, that even somebody of that even if somebody of that caliber can still fail to see a certain connection that I'm going to hopefully show to you, that it kind of brings out how difficult it can be to kind of understand somebody's place in the history of a particular subject. So, yeah, pretty much every physicist, with some exceptions, just think, yeah, Goethe's got nothing to do with science. It's not science, it's something else. And even people who are for Goethe, they also seem to agree that what Goethe's doing, that's not mathematical science. That's not what Newton's doing. That's something completely different. So Bortoft is just, I could have chosen pretty much anyone who's written about Goethe. Also important is that Bortoft talks about the mathematical, or the one-sided mathematical approach. Now, he doesn't just mean the application of mathematics. He also includes Francis Bacon, that didn't do anything mathematical, but Francis Bacon still looked at the example, or his method was still based on the general mathematical method, which I'll talk to you about now. So Bortoft's kind of claim here isn't about mathematics per se, but a mathematical style of thinking. So what is the mathematical style of thinking? So mathematical method. So I've chosen Pappus, as I said. He was a very influential mathematician. He has a huge influence on Newton, Descartes, and he was late antique, 3rd or 4th century, we're not sure. And he is the first person that we know of that has spoken explicitly about the mathematical method as having two parts to it. One part called analysis and the other part called synthesis. And so this is, from a historical point of view, a very important text because it gives us some insight onto what antique mathematical practice was really like. So what is this mathematical method? So Pappus says, for in analysis, we assume what is sought as if it had been achieved, and look for the thing from which it comes about, and again what comes before that, until by regressing in this way, we come upon some one of the things that are already known, or what occupy the rank of a first principle. We call such a method analysis, that is, solution backwards. So analuo means literally to undo. So in Greek, you would analuo your sandals. You'd analyze your sandals when you take them off. So analysis in the mathematical method is when you start from somewhere and then you look at, you kind of undo it backwards. You kind of So in mathematics, if you want to prove something, you'd first have some kind of conjecture or postulate, and then you'd see if you can then step back, step by step, to some known principle or some known axiom. So it's this process of regressing backwards, of stepping backwards to a first principle. So for instance, one of Euclid's kind of postulates, would be an example of a first principle. So that is analysis. So you're moving from a conjecture backwards to a first principle. In synthesis, by reversal, we assume what was obtained in the last analysis to have been achieved already, and by arranging in their natural order as antecedents what were consequents in the analysis, and by putting them together, we reach the goal of the construction of what was sought. And we call this synthesis. So what he's saying here is that once we have our analysis, we come back to a basic principle, then to make our proof, we then just turn the whole thing around. So we start off with a conjecture. If we can argue backwards to a known principle, we can then turn the argument around and then argue from the known principle and prove the thing that was initially a conjecture. So again, the basic idea is analysis. You go from what you have in front of you to a first principle. And then a synthesis is you go from the first principle, then back to what you want to prove or what you want to demonstrate. Okay, so this is the basic two-step mathematical process. So analysis was used for discovering proofs. And once you had discovered a proof with an analysis, you would then demonstrate your proof. You would construct your whole proof based on the method of synthesis. So with synthesis, you'd start with your basic principle, and then step by step, you would then prove some theorem out of that. So Euclid's Elements, for example, is examples of lots of synthesis when he starts with a basic postulate and then he shows, that some theorem then follows from that. Okay, so that's the mathematical method. So there's a lot of evidence that Aristotle and Plato both would have known of this mathematical method, and probably with this name. So Plato's Meno, for example, describes something very much like this without this particular name. And Aristotle uses the term analysis when he's talking about his natural science, and which would mean that he's expecting his audience to be familiar with the mathematical method of analysis, which he is then applying to something else. So, the basis of modern science in Aristotle's work most likely comes from these kinds of practices of finding proofs through analysis and then demonstrating proofs through synthesis. All right, so we will, jumping forward a century and a half from Pappus to Newton, just over a century actually. So Newton says at the end of his Optics, so a couple of pages from the end, he has, like a page on methodology. That's probably the most important statement we have about Newton's methodology in all of his works, not just his color works, but his work on gravity as well, his Principia. So Newton says, as in mathematics, so in natural philosophy, the investigation of difficult things by the method of analysis ought ever to precede the method of composition or synthesis. So composition is just Latin for synthesis. This analysis consists in making experiments and observations, in drawing general conclusions from them by induction, and admitting of no objections against the conclusions, but such as are taken from experiments or other certain truths. And then he has this claim, which we'll then come back to in the final part of this talk, that for hypotheses are not to be regarded in experimental philosophy. So Newton is presenting his method as being the mathematical method, and that then excludes hypothesis. So a hypothesis would be a conjecture that then isn't based on any demonstration. So a classic example of a hypothesis would be something like Descartes and his theory of color. Descartes just said, the color that you see is because the light is composed of particles that spin with a certain speed. So he just says that. No proof of that. He doesn't demonstrate that. That's just his starting kind of proposition. And Newton is rejecting that kind of approach to understanding natural phenomena. Newton is saying you need to demonstrate your claims by starting with the experiment, doing experiments, and then coming to general principles. He then carries on. By this way of analysis, we may proceed from compounds to ingredients, from effects to their causes, and from particular causes to the more general ones, until the argument end in the most general. This is a method of analysis. And synthesis consists in assuming the causes discovered and established as principles, and by then explaining phenomena proceeding from them and providing the explanations. So analysis, you start with a cause, you start with an effect, a phenomena, and then if you analyze that, that's going to take you to the cause. Also, if you have something compound, the analysis is going to take you to the things, the ingredients that it's made out of. Yeah, and this is the method that he used for his optics and his universal gravitation. So this is why he's kind of expressing it quite generally. And then synthesis is then the opposite. Synthesis is when you want to explain something like the colors of the rainbow. You can then use your basic principles and demonstrate that from your basic principles that the particular phenomenon that you're interested in can be explained by the basic principles. So again, we have this idea that analysis is going to help you discover something, in this case, the basic principles, and synthesis is then going to allow you to explain something. So in mathematics, you know the basic principles, but you're trying to find the proof. In Newton's method, that's turned around. You start with what you know, the phenomena, and then you, in a way, through the analysis, you then go, you regress to the basic principles. So you go from the effect to the cause. So there's an important difference here between using the mathematical method of analysis and synthesis for finding proofs and demonstrating, or for finding theorems and demonstrating theorems, and finding basic principles about the world and then demonstrating phenomena that are related to them. Okay, so we're going to now just to look at a few examples. So Newton famously darkened his room, made a small hole in his window shutters, shone some light through, and then he put the beam of light through a prism, and rather than getting a round circular white image of the sun on a wall, he had this colored spectrum before him. So Newton thought, great, I've analyzed the white light into its component parts. Because one of the things of analysis, he says, it goes from what is compound to what is simple. I think from compounds to ingredients. So we start off as white light as something compound, and then we analyze it into its ingredient colors. So this would be an example of analysis. And synthesis is then when you do the opposite. So on the top drawing, on the right-hand side, we have the light coming in through the window shutter, is then being analyzed into its different colors, and then it passes through a lens, PT, and then the different colors are then focused again at the point O on the left, and the different colors are then synthesized back into white light. So at point O, you've lost all colors and you have white light again. So we first have analysis, we have a lens, and we have synthesis. of the ingredients of the sunlight, of the constituent parts. On the bottom, we have the case where if you shine the light from the sun through a prism onto the wall, if you then look at that image, that colored image on the wall through a prism of the same shape and the same material, the colors will then disappear. So the prism, so the light, so what's happening through the first prism as the sunlight goes through it onto the wall is then the reverse happens when the light is reflected back into the second prism. So the first prism is analyzing, the second prism is synthesizing. So Newton also did his famous experimentum crucis. So how do we know that we've reached the basic principle? So, or rather, what is the basic principle of light or color? What's the basic principle of color? So Newton, he shone the light through his window. It went through a prism. It created a color, and then he selected with two boards, and a hole, big G on the right and little g on the left. With those two holes, he selected just one ray. So into the second prism, you had one selection of the image we saw before. So we have this image here, and then the hole selects, let's say, a tiny bit of the yellow and passes that through a second prism. And then that yellow ray stays yellow, goes through the second prism, and falls onto the wall. And keeping the two boards in place with the two holes, so that from the second board, DE, all and everything to the left, no change happened to the experimental apparatus. But Newton moved the first prism so he could select different colors. And what he found was that when he selected different colors, the place that each color fell on the wall on the left moved. So what he found was when the color changed, the position of the beam of light on the wall moved. So Newton showed that there was a kind of correlation between the color that the beam of light had and the amount that it was changed by the prism. So he could associate one property, the color, with a different property, the amount that the light was bent, the refractability, as we'd say today. So because the second prism didn't change the color of the light, green light in, green light out, yellow light in, yellow light out, Newton concluded that the light was fully analyzed. It couldn't be split up anymore. And therefore he'd found he'd found his basic principle. He'd done his analysis from the phenomena being the nice colored picture here. He analyzed that further with the second prism and found that that can't be analyzed any further. So his principle that his basic principle was that to every color belongs a degree of refrangibility, as he called it, a degree to which that light was bent. So that was his basic principle. So Newton was very pleased about himself, and then he could use his basic principle to explain other things through synthesis, like the color of the rainbow, stuff like that. Okay, so here's a little painting by Sasha Grusha of Newton's Experimentum Crucis. It does actually work like that. I have actually managed to do it with very little experimental apparatus. It can be done. So if on one sunny day you really don't feel like going outside and you happen to have a couple of spare prisms, then do try that out. So Newton on the left, he's holding a prism in his hand. The light of the sun is shining through a board with a hole in it. And then the board in the middle of the room is just selecting the color yellow. The color yellow is then being refracted by a second prism and is being projected up onto the wall on the right. Okay, that was Newton. So now we're going to look at Goethe. So far we've looked at Newton and we've looked at Pappus, and we've seen, okay, we can see similarities between their methodological description. There is, and there's also some differences as well, but mainly we're seeing a certain kind of methodological similarity about how to do science, how to find basic principles, and then how to use basic principles to then demonstrate or explain something. So Goethe says, this is in the didactic part of the Farbenlehre, his theory of color. So this is just after he has spoken about the atmospheric colors, the sunrise, the sunset, the yellows and the reds, and then the blue of the sky. And then he's just about to talk about prisms. He then has this little kind of methodological reflection that's very important for understanding Goethe's method. So he says, in general, events we become aware of through experience are simply those we can categorize empirically after some observation. These empirical categories may be further subsumed under scientific categories leading to ever higher levels. In the process, we become familiar with certain requisite conditions for what is manifesting itself. From this point, everything gradually falls into place under higher principles and laws, revealed not to our understanding through words and hypotheses, but to our seeing through phenomena. So again, we find reflected what we saw before in the earlier essay, The Experiment as Mediator. So we start off with these kind of empirical observations, and then as we then work with them, we can then start to see what conditions bring about which phenomena, and then we can start seeing connections. And we start to, and then things kind of fall into place, and then we start to see these higher principles. And it's interesting, he says, they're not revealed to our understanding, but to our seeing. So again, we have a reflection of what he said before, when he said that these relationships, we see them. They're fully perceptible. The English that I'm quoting here is from Douglas Miller, his book Scientific Studies, which has a collection of these essays as well as Goethe's work on plants and color. But so he translated Anschauung as intuitive perception. I find that quite misleading, so I've changed it to seeing. So I just thought it was worth pointing that out, and also makes it easier to see the connection to what Goethe said before. So, and then we come to the very famous claim or statement. We call these phenomena archetypal phenomena, Urphenomena, because nothing higher manifests itself in the world. Such phenomena, on the other hand, make it possible for us to descend, just as we ascended, by going step by step from the archetypal phenomena to the most mundane occurrence in our daily experience. So again, we see this picture of moving from our everyday world, experience as it presents itself in a kind of unregimented way, through a process of looking for the causes and connections between things. We then come to these Urphänomen, these archetypal phenomena, which we can see, but which allow us to also explain then, the empirical world. So these Urphenomena, these archetypal phenomena, they have the same principle. They function as principles. So again, we have this process of analysis where we are going from our everyday world, our kind of empirical consciousness, if you like. We are moving through a scientific process to some basic principles. And once we have these basic principles, we can then use those basic principles to then explain the world around us, like the rainbow, the colors of things, the setting sun, the blue of the sky. So just so you don't think that I'm putting words into Goethe's mouth. So in an essay, he published an essay called Analysis and Synthesis. In 1829, so towards the end of his life, so 19 years after he published his theory of color, he published he published this short essay, Analysis and Synthesis, and there he's very explicit. He said, to develop our theory of color, we used the analytic approach. Insofar as possible, we presented every known phenomenon in a certain sequence so that we could determine the degree to which all might be governed by a general principle. So again, Goethe is explicitly saying, analysis is this process by which we present lots of phenomena, every known phenomena, he says, and then we use this process to then come to a general principle. So the reason I'm kind of being quite kind of explicit about this is there's a tradition going back to Schiller, actually, that claims that Newton and modern science does analysis and Goethe does synthesis. So Schiller started that. Schiller died 5 years before Goethe got to publish his theory of color, sadly. But somehow that idea has persisted that Newton does analysis, scientists analyze, and Goethe synthesizes. So this idea that experimental science does analysis and Goethe does synthesis is part of this general idea of conceiving Goethe as completely separate from the scientific canon. So Goethe has this completely, this poet comes out of nowhere and just comes up with this this new poetic approach to know nature, or this new kind of intuitive approach to know nature that somehow kind of diametrically opposed to science up until that date. So that general picture, many of you may be familiar with that. And our good friend Henry Bortoft also subscribes to that picture. So in his works, there's a number of statements where he says, Goethe does analysis, Newton does analysis, Goethe does synthesis. And I just wanted to, just show explicitly that that's not how Goethe understood his methodology. Okay, so let's see what Goethe does. How does Goethe put this into practice for his study of color? So here we have a series of experiments. So here we have an example of forming a series. So picture number 3 is roughly what Newton's spectrum was. And so what Goethe did was say, okay, what happens if we open up the slit? What happens if we close down the slit? And what we do is if we move left, we're opening up the slit. So as we move left, the slit gets wider, and then yellow and the cyan get bigger, but the green disappears until if we open it all of the way, then we have white in the center. So it's only when the yellow and the cyan come together that the green appears. So this is around number 3. Around number 4, as it gets even more closer, as it gets even more, as it gets even smaller, the yellow and the cyan overlap completely, and then we have just green. So actually, nowhere in the sequence of closing the slit do we actually find Newton's spectrum with a nice orderly kind of lines of 6 colors, or sometimes 7. So that kind of neatly ordered spectrum of 7 colors is a scientific construction. It doesn't actually exist. You can't observe it. And that's one of the things that kind of made Goethe annoyed about Newton. So Goethe's approach was that if you opened up the slit, you had these 2 simple edge spectra. So you can see these on the right-hand side. So in a Beiträge zur Optik, he discusses this very much. And for him, it's a simple boundary between light and dark makes 2 simple colors, either red and yellow, or if you turn the prism upside down, blue and cyan. And if you bring the two boundaries together, the yellow and the cyan together, as we saw, you get green in the center. So then we have the spectrum on the just to the left. So which is, you know, the picture of the sun that was going through Newton's prism. And you can also do the opposite. You can shine a shadow through the prism, and then the opposite sides come together, and then you get magenta in the center. So this is what it actually looks like if you photograph it. So on the left, we have the image of a sun shone through a prism, and on the right, we have a round shadow with a light background shone through a prism. So for Goethe, these are just two different ways of bringing together these two simple edge spectra. And then Goethe kind of presents all of that in a kind of overview here. You can see on the left-hand side, it's for the sun shining through the prism, and on the right-hand side, it's a shadow going through the prism. So for Goethe, the basic components are not the spectrum that Newton started with, but the two edge spectra. So for Goethe, it's the phenomenon on the right-hand side is the Urphänomen. That's the basic principle, the archetypal phenomenon. And then from that archetypal phenomenon, you can then explain Newton's phenomena, if you like. So, for example, if we go back to the image on the right-hand side, so we have yellow next to white and we have red next to black. So we have a light color next to white and a dark color next to black. If we go to the other edge spectra, we have cyan and blue. The blue it's more of a kind of greeny blue. You can see it better here. So we have like, yeah, here's better. If we look on the left-hand image, we have a blue on the boundary, on the left-hand boundary between light and dark, we have blue, which is dark color, and then a cyan, which is very light. And then we have yellow, which is light, and then red, which is dark. So if we take the edge spectra as an Urphänomen, as a basic principle, then we have a light color and a dark color next to black, dark color next to black, light color next to white. So Newton's spectrum for Goethe has to be dark color, light color, dark color, light color, dark color. And if we look at it, it is. So we got blue, violet, then we got the cyan, then we got the green, the yellow, the red. It's maybe a bit easier to see with this one. So we can see that with the spectrum on the left, we've got dark color, light color. The green gets a bit darker, not so easy to see because the cyan's nearly gone. Then we've got yellow, light color, and then red, a dark color. On the right-hand side, we reverse the situation, then we have the opposite. We have a light color next to the white, then a dark color, the red you can just about see, and then magenta, a light color, and then blue, a dark color, and then cyan, a light color. So Goethe's edge spectra can explain the structure of Newton's spectrum. So just to finish this section before going on to the final part, Goethe's method of analysis, we can say contains the three stages that we looked at before. We have the manifolding, we have the scene connections, and we have the basic principle, or the archetypal phenomenon. And in the case of the prism experiments, the edge spectra with the archetypal phenomena, and Newton's spectrum was then a composite. So an analysis of Newton's spectrum would then show the edge spectra. Okay, so what does this mean for Goethe's critique of Newton? So Goethe can't really be critiquing the fact that Newton is applying mathematics, because Newton doesn't apply any mathematics. Newton's basic principle is that, you know, a certain color has a certain degree of refrangibility or a certain amount of being bent. Now, you can use that to then mathematize color, which is what indeed happened, but it's not itself a mathematization of color. It's an application of the mathematical method to the realm of color by analogy. So Goethe can't be accusing Newton of that, because that's what Goethe is doing too. Goethe is also applying the mathematical method to the realm of color by analogy. Goethe also can't be accusing Newton of applying the mathematical method or the mathematical style of thinking, because that's just what Goethe is doing too. So what is Goethe's critique? So Goethe says, in this sense, we consider the error which has sprung up in scientific research on color to be a grievous one. A derivative phenomenon, an abgeleitetes Phänomen, has been placed in a superior position and an archetypal phenomenon in an inferior one. Moreover, the secondary phenomenon itself has been turned upside down by treating what is compound as simple and what is simple as compound. So before we kind of go into what that means, even the language is, Newton is confusing what is simple with what is compound. So these, Newton himself talked about analysis as going from what is compound to what is simple. So what Goethe is doing is not saying, Newton, you shouldn't be using analysis. He's saying, you, Newton, didn't do your job properly. You didn't do what you said you were going to do. And also he says a derivative phenomenon has been placed in a superior position. So something that is derived is something that comes after a synthesis. So something that is a synthesis from a basic principle is being placed in a position of a basic principle. So again, he's accusing Newton of just getting his method muddled up. He's putting the wrong things in the wrong places. What does he mean exactly? So if we come back to this image, what is compound, what is simple? Newton thought his spectrum, which is on the far left, he thought that was something simple. That's as far as analysis can take you. But Goethe said, no, on the right-hand side, I've analyzed the image on the left-hand side, and I get the image on the right-hand side, the two edge spectra. So Goethe is saying that Newton stopped analyzing too early. He didn't analyze his full spectrum on the left-hand side. He didn't analyze that into its component parts. He treated what is composite, the Newtonian spectrum, as something simple. And that is what Goethe is accusing Newton of. So why is that bad, you might ask? Newton's got one theory, Goethe's got another theory. Yeah, okay, surely they can live happily together in a pluralistic scientific universe. So it's not that simple. And it's not that simple, not because of Goethe, but because of Newton. So Goethe says of Newton, he says, although there has hitherto been a general belief that the nature of color was understood, and people have imagined that it was being accounted for by means of a trustworthy theory, this was by no means the case, for it was hypotheses that were being accepted as fundamental. So the charge here is that Goethe is saying Newton is claiming to present a theory, but actually he only presents a hypothesis. So for us, this is like, what's the difference? Theory, hypothesis, tomato, tomato. Aren't they just getting upset about each, or isn't Goethe just been getting upset about Newton's language? So we'll see that that's not true. Newton took his language very seriously. So when Newton first published his paper, A New Theory About Light and Color, he then got a letter from a color scientist on the continent, Ignace Gaston Pardies. He was a Jesuit, I think in Belgium. I can't remember off off the top of my head. And he said, he thought, I'll start off before I come with my objections to Newton's theory. I'll start off by kind of saying something nice. And he said, I've read Mr. Newton's very ingenious hypothesis of light and colors. And this alone annoyed Newton immensely. Newton replied by saying, I do not take it amiss that the Reverend Father calls my theory and hypothesis, inasmuch as he was not acquainted with it. But my design was quite different, for it seems to contain only certain properties of light, which, now discovered, I think easy to be proved, and which, if I had not considered them as true, I would rather have them rejected as vain and empty speculation than acknowledge even as a hypothesis. So Newton is making this very strong distinction between a hypothesis and a theory. And basically, it comes down to this. An hypothesis can be wrong. An hypothesis is a conjecture, it's an assumption. But a theory is necessarily true. A theory has been demonstrated by analysis. So analysis, when applied to color, when applied to the movement of planets, it doesn't give you a hypothesis. It doesn't give you a theory in the modern sense. It gives what Newton considered to be a demonstration that is as certain as mathematics itself. So just as 1 + 1 = 2, just as certain is Newton's theory about color. So Goethe's claim against Newton is not that he had an interesting theory, but there's another theory too, Goethe's theory, which is also interesting, but rather he's saying that Newton, he took the method of analysis, he realized that it could provide better than an hypothesis. It can do something better than a mere theory, as would say in modern language. It can demonstrate the truth. It can demonstrate scientific truth. Goethe thought that was right, but Goethe just thought Newton hadn't applied the method correctly. So basically, Goethe sees himself as taking Newton's method of analysis and applying it properly to give a theory of color that demonstrates the truth of something in the way that Newton had thought his theory had. This is from Newton's Optics. He's very explicit. My design in this book is not to explain the properties of light by hypothesis, but to propose and prove them by reason and experiment. So Newton wants to demonstrate the truth of his theory of color. And so by Goethe saying it's not a theory, it's a hypothesis, Goethe is saying, Newton, you have failed to live up to your methodological claim. But Goethe, by saying, I have also done an analysis of color, he is saying that in a way, Newton was right to have that methodological claim. He had the right method, but he just didn't apply it properly. So I will end my presentation with a well-known quote from Goethe. It's one of the maxims. The ultimate goal would be to grasp that everything in the realm of fact is already theory. The blue of the sky shows us the basic law of chromatics. Let us not seek for something behind the phenomena. They themselves are the theory. So hopefully, if I have been in any way convincing in the presentation I've just given, hopefully you can see this as, in a way, Goethe endorsing Newton's goal, but himself taking it one step further. So to come back to my initial question, was Goethe a Newtonian? I would say yes, he was, but we have to understand Newton very differently as a modern scientist. The physicist Carl von Weizsäcker, he once said, we are students of Newton and not of Goethe. But that's not true. We're not students of Newton. Goethe was a student of Newton. Our science took a very different direction. Okay, so that concludes my talk. I just wanted to finish by saying that, that if I've been convincing, then applying Goethe's own method to the history of science shows us that Goethe is in a way a true heir of the scientific method that was developed out of mathematics in antique Greece, and that we shouldn't be separating Goethe off as being somehow outside of the scientific tradition. And on that note, I will end my talk. So,
Troy, thank you for sharing the depth and precision of your research on Goethe there. We don't have any questions yet from participants. If you do want to ask Troy, then pop it in the Q&A box. Troy, I know in the meantime that you've got a book out, and that's been published by Brill. I wonder, whilst people are kind of gathering their thoughts and formulating their questions, if you can you give an introduction to that?
Sure, yeah. So this book just came out. I just picked it up from my little pigeonhole in Humboldt University. This was together with Olaf Müller. He's a professor for philosophy of science at Humboldt University, and a couple of my colleagues there. And this book really looks at, well, the title is Goethe, Ritter und die Polarität, so Goethe, Ritter, and polarity. And it really, the aim of the book is to show that people like Goethe, people like Ritter, the idea of polarity, it wasn't just some strange romantic kind of flight of fancy, but actually gave us things like, ultraviolet radiation, rechargeable batteries, electromagnetism. And so in a way, it by looking at this period in a more circumspect way, we can actually see that that romantic science played a very, very important role in our scientific history. And so the last part of my talk, I give a much longer version of that in the book, for those of you that like to read in German. If anyone wants, I have like an English draft of that. I'm happy to share that privately. So that's, and then also the In Dialogue, which was a collaboration between the Field Center Journal and the Holistic Science Journal. I have an essay in that. You can download it free online, and there I talk about Newton, Goethe, and the mathematical style of thinking, and the connection with Henry Bortoff. So that's where I'm drawing most of the material that I've covered in the talk from. Some questions.
Questions are coming in. So first of all, there's a question from Dietrich, who's got a question. First of all, you restricted Goethe's work to morphology, while I think he did more than that, and then discussed his color work. What do colors have to do with morphology?
Yeah, that's a great question. So morphology is associated with Goethe's work on plants. Mm-hmm. And today we generally think of morphology within that context. Goethe considered all of his scientific work to be to employ the morphological method. So I was using morphology in that loose sense. So morphology just as another way of talking about Goethe's scientific method. It's interesting. So if we look at historical linguistics, we talk about the morphology of a word. That comes from Goethe, from from Goethe's application to plants. As I said before, Wittgenstein said, when I do philosophy, I'm giving the morphology of the use of a word. So I'm using morphology in that kind of promiscuous sense, rather than in the narrow sense of applying to plants. So yeah, sorry for not being clear about that.
Great. So Dietrich, I hope that answers your question. Then there's a mysterious question from John, who's, here it is. Is there a phenomena that Goethe's theory of light can explain which Newton's theory cannot? And if so, why would this not be discussed, accepted by modern Newtonians? Aha.
So the funny thing is, so just from the point, let me just check off before I go off on one, just check that I've got the question clear. What is there a phenomenon that Goethe's theory of light can explain which Newton's theory cannot? And if so, why is it not? Okay, right. So I mean, the basic, Newton's theory cannot explain why red is next to yellow in the rainbow. It cannot explain why, for example, in between yellow and cyan in the rainbow, you have green, which just happens to be the subtractive mixture of yellow and cyan. It cannot, So the order of the rainbow, the structure of the rainbow for Newton's theory is just incomprehensible. In fact, it shouldn't have a structure. So also, for example, Goethe's theory can explain why the rainbow goes dark color, light color, dark color, light color, dark color. And Newton's theory cannot explain that. So for Newton's theory, that's just a brute fact that just happens to be the case. What else? In fact, Newton's theory in some ways, this has been remarked by a number of people. Newton's theory can't really explain anything about color in some sense. Why is white the lightest color and not some other, why is white the lightest color and not some other color? Why don't we have a dark yellow? We can have a dark blue, but we can't have a dark yellow. Why? So these are questions from Wittgenstein's remarks on color. So Wittgenstein picks up on statements that Goethe makes about color, and then he realizes that actually you can't explain them with any kind of Newtonian theory about color. Why can't you have you can have a transparent red, but you can't have a transparent white? Why? So these are the kinds of, so it's these kinds of questions that Goethe can explain that Newton can't. And the thing is, and if so, would this not be discussed, accepted by modern Newtonians? The thing is, there are no modern Newtonians. Evan Thompson wrote a book in the 80s. It was his PhD thesis called Color Vision, and he said, the one thing that color scientists today agree on is that Newton was wrong. They don't agree on pretty much anything else, but they do agree on that. So in some ways, since the 60s, so the work of Edwin Land, and then funnily enough, computer vision in the 80s and 90s, when they tried to train computers to see colors, and they realized that a kind of Newtonian mapping between color and wavelength just absolutely failed for anything but the most basic kind of cases. Now, the interesting thing is the one thing Newton can explain probably better than anyone else is rainbows. But it can't, so in a way, the one thing that Newton looked at, his theory can explain fairly well, but it can't explain pretty much anything else. Like colored objects are the biggest problem. So this is when Goethe actually does quite well, but is that when we see a green object, what we're actually seeing isn't green light reflected off that object, but the absorption of that object by the complementary color. So seeing objects is deeply tied in with the idea of polarity. When we see a yellow object, what we're seeing is that the light is taking out the blue. Sorry, the object is taking the blue out of the light. So a colored object, what we're perceiving is actually how that object takes the complementary color out of the light. And that kind of Goethean polarity is fundamental to understanding color vision. And also, I mean, since Helmholtz, really, the kinds of phenomena that Goethe were interested in, after images, colored shadows, those have become, the standard kinds of phenomena that color scientists look at in order to understand color. Yeah, hope that wasn't too long. So there's this, it's funny. There's this kind of myth that kind of somehow Newton was right and Goethe was wrong, but yeah, it's strange how these things kind of stick around.
I have a question. If there,
yes,
the other one to be answered. Well, thank you very much. First of all, I found it absolutely convincing, actually. At least one of the stories, I think you told two or wanted to tell two. One is sort of the relationship between Goethe and Newton, but he also wanted to apply, what was it? Morphology or a Goethean approach to the history of science. And that bit wasn't that clear to me. I mean, it seems that you have to, maybe you could tell it, maybe you did, I'm not sure I got it, but you need some kind of phenomena that you're studying, and then you need to see connections, and then you need the basic principle. And I'm not sure, for instance, what the basic principle you uncovered is. I mean, could it be something like Goethe is actually Newtonian, which would be nice. I mean, that part I agree with, but I didn't it wasn't clear to me exactly how you applied morphology to the history of science.
Yeah. So that's a really good question. So the basic principle for me is that you have this two-part method, analysis and synthesis, and then I only gave 3 examples, but the thing to do would be to kind of have, to kind of bring more and more examples from the history of science, and then look at, and then see the kind of different ways in which that then finds expression in different methodologies. So the basic principle would be this kind of 2-stage method. First, analysis to basic principles, and then explanation using synthesis.
So, but do you think that's a basic principle for the whole history of science?
I think it is.
That's what I do. Yeah. Okay. Nice.
Fine. Yeah, and I think that goes back to Aristotle, and he just said, for Aristotle, that was because of how the world is. So Aristotle said, what is first for us isn't first for nature. So we need to go from what is first for us, the world as it presents itself to us, to what is first for nature, the basic principles. And so therefore you need some message, the world, you need some method to go from what's first for you as a knower to what's first for nature as a being. And so, how you cash that method out, there's many different ways of doing it, but that basic principle is the same. And the basic idea is that nature isn't going to give you everything in one go. Nature is going to make you work for your knowledge.
But how about science that works with hypothesis then? Isn't that science? I mean, did the history of science end with Goethe and Newton? So yeah, that's So that's also science too, right? So I'm not claiming this is the only thing science does, but it's one basic principle that you could follow back through the history of science. I mean Descartes. So in a way, the idea behind the hypothesis. If we take Descartes, he's the one that Newton kind of rebels against. So Descartes took mechanical philosophy. He said nature has to follow these mechanical laws,
because they are basic principles for the human mind. So in some ways, even a hypothesis has this kind of structure. What comes first? Yeah.
Good, thanks. Yeah.
And yeah, and in terms of applying Goethe's method to the history of science, I mean, I think this is what good historians of science just do anyway. So I think in the humanities, we're actually applying Goethe's method all the time. So yeah, and Wilhelm Dilthey was massively influenced by Goethe. So it's not so surprising that the methods in the
that was actually quite striking. In a sense, Newton isn't doing science. I mean, he shows that the phenomena themselves are sort of, I don't know, exhibiting the nature of science, nature of knowing somehow. You know, and that's pretty radical.
Yeah, I mean, I think Newton was a Goethean or Goethe was a Newtonian, but in this kind of Aristotelian sense, that nature demonstrates its basic principles. Nature can show itself. So there's this, yeah. So in some ways, it's not really Goethe that we're not understanding. It's actually Newton that we're not understanding. And so having a nice series then from, I mean, one could put in Descartes and stuff. It kind of, the more you have in the series, then the kind of clearer it is what's going on. And so, you see, actually it's we project into Newton what Descartes was doing, which was the very thing that Newton was actually rejecting explicitly. So yeah, so this is the kind of benefit of having a nice series, which is, and then you have your series, which is step one. You start to see connections, which is step two. So
Troy, thank you very much. So what I'd like to do now is just want to thank Troy, first of all, for all of your research and for sharing that, and also for the conversations where always more emerges. And then there's a couple of announcements when you can join us again on Thursday, on Thursday, I'm just going to check that. That is... Sure, have you got a screen share there?
Yeah, I've just shared that. Bear with me. Screen sharing is surprisingly difficult. That should be working.
There we go. Okay, so please join us again, and that is going to be on Thursday, the 2nd of September, again at 4 p.m. That's GMT. That is Restoring the Vertical, and that is brought to you by Jonathan Code, The Contemporary Relevance of Schumacher's Guide for the Perplexed. Jonathan is a lecturer in sustainable land management at the Royal Agricultural University in Cirencester, and is senior lecturer for Crossfields Institute. So if you're interested in what the contemporary relevance of Schumacher's Guide for the Perplexes, join us on Thursday, the 2nd of September at 4 p.m. You can also join us in person at Schumacher College, October the 1st to the 3rd, for the Holistic Science in Dialogue Conference. The conference, again, is a collaboration, not only this time between the Field Centre and Schumacher, but also with the Holistic Science Journal. And there, the conference focuses on and builds on the contributions to holistic science made by 3 key figures. That is Henry Bortoft, Margaret Colquhoun, and Brian Goodwin. And you can join us for presentations, for research panels, and also for discussions. We will look back, we will look forward. Booking is now open. It's on the Dartington website. I think Troy has just shared the link there, so you can read more about it. We've got confirmed speakers of Emma Kidd, Judith Sassoon, Claudio Staran. And then we also have 2 keynotes. We have Isis Brooke, she will give a keynote on engaging with the plant realm. And then Harvey Schulman, the Spinoza of Totnes, Brian Goodwin, and the deductive science of life. So I want to say thank you very much for tuning in, depending on where you're tuning in from. On behalf of Schumacher and the Field Center, I'd like to wish you a very good night, day, or evening.